Alright, hey guys. Sorry to be missing another one of your classes. Unfortunately, doctor's appointments don't always coincide with the days that we need them to. So, in order that you guys are not going to miss any of the lesson, here it is. So, you should have already completed the drill, and we are going to move on to some of the basic properties of logs. In order to get into some of the basic properties of logs, there's a couple of things that we need to review with you guys. So, first thing is something that you may not have seen before, but I need to make sure that you understand that if I were to give you the square root of x, if we want to put that into some kind of an exponential notation, a square root actually means the same thing as a 1/2 power. Okay, we're going to go much more into depth as to the powers of roots and everything like that and how they work, because they're all fractional roots, but you need to know that one in particular in order to do the stuff that we're going to do. So just know that if you see a square root, it means a 1/2 power, or vice versa. If you see a 1/2 power, it means it's the square root of that thing. So an example of that would be 9 to the 1/2 power is the same thing as the square root of 9. It works both ways. Okay, and these notes here you can take on the back side of this packet that you guys have. There's a blank piece of paper. There's a blank sheet of paper on the back there. Couple other things that we need to review, because remember in the last class I told you guys that logs are exponents. Well, they follow all the same exponential rules when it comes to multiplication of things with common bases and things like that. So a couple of things to remind you guys. If I have x to the 4th times, that is a times, x squared, I have common bases. The base is both x, and the exponents are 4 and 2. The rule is that if I multiply those two, I'm going to get x to the 6th, because what I do is I add the exponents. So let me break that down a little bit for you guys. What this means, x to the 4th, is x times x times x times x. And what x squared means is x times x. Well, I'm multiplying those two things together. So if I multiply all of those out, we would get x to the 6th. I would have 6 factors of x. So in general, the shortcut for that is if I have a common base, whatever the base is, raised to some power, multiplied by another common base raised to a different power, in order to get those two things multiplied together, it is the base raised to the sum of the exponents, you adding the exponents. If you can think of it like this, it makes it a lot easier to remember the rules. The reason we do it that way is because while you could really easily write out those 6 x's right there, you don't want to do it if the exponents get really, really large. We don't want to write out, 17 x's and another 34 x's or something like that. You would just know you're going to add the exponents. Likewise, if we have this drives me nuts. Okay, sorry about that. Likewise, if we have division, so let's say it is x to the 4th divided by x squared. Well, actually that's a bad example. Scratch that. Let's do x to the 6th divided by x squared. Once again, the general idea is if I wrote that out, I would have 6 x's multiplied on top, 2 x's multiplied on the bottom. And when you start canceling them out, really dividing those two things together and getting ones, you're left with 4 x's on the top. So what you get is x to the 4th. So what you should see is what you're doing is you're really taking 6 and subtracting 2. Okay, rules of exponents. When you divide common bases, you subtract the exponents. So in general, it would be some base raised to the m divided by some base raised to the n, would equal that common base raised to the m minus n. You're going to subtract the exponents. Okay, I'm going through this for a reason because you need to know these properties. The last major property that we need to know is if I have something like x squared to the third power. Now I have something which already has an exponent and I'm raising it to another exponent. If I have something like that, again, what this actually means, x squared to the third power means it's x squared times x squared times x squared, times x squared. That's what it means to raise something to the third power, multiply it by itself 3 times. Well, if you were to write all those out, you would have x times x times x times x times x times x. You would have 6 of them. So that would be x to the 6th. And hopefully what you can see to get a 6 is you're multiplying those exponents together. So when you have a power raised to a power, an exponent raised to another exponent, you multiply them. So in general, if I have b raised to the m power raised to the n power, it is b to the m times n power. So you multiply your exponents. All right, those are the properties we're going to need in order to be able to do the basic properties of logs, because if you remember, logs are exponents, so they're going to follow the same properties. All right, unfortunately, the copies that I was given here had everything filled in on this sheet, so it's not like I can just walk you guys through this and have it all filled in and have you fill it in. It was there and we couldn't get rid of it because it was permanently put in a PDF form. We couldn't erase it, so we're just going to have to go with this. So what you can see on your sheet is that I have something which is an exponential in form here. The example is 2. That's a base, but it's being raised to an exponent, which is a log. Well, again, let me erase those lines so you can see it. Remember that logs are exponents. So if you can kind of see this little arrow here, it's kind of telling you where we would go with this. If you kind of just ignored that that was there for now, log of 2 base 4, you could rewrite that and say log of 4 base 2. Remember, it's 2 to what power gives me 4? Well, it would be 2 squared gives you 4. So the log of 4 base 2 is actually equivalent to 2. So this is 2 raised to the 2 because all of this becomes that 2. And so then 2 squared, of course, is 4. You can simplify it. And the second example over here on the right says that if I have a log, I'm starting with a log now, and that log actually has an exponent on it. So it's the log of 3 base 3, but the 3 is actually raised to the second power. So this part right here, this argument, is 3 squared, which is 3 squared, of course, is 9, which is what they're telling you here. And then you're asking yourself, 3 to what power 2 gives you 9? So that's why this whole thing here, this whole thing simplifies to 2. And hopefully after a little while you're going to start to see the pattern here on what's happening. And if not, hopefully by the end of this I can explain it to you. So let's see. Let's go through example 1. I'm not going to do all of them, but because they're already done for you, but I'll go through a few of them. Example 1, 3 is the base, 3 is the base. I'm going to look at the log, which is log of 9 base 3. That says 3 to what power gives me 9? Well, that power is 2. So 3 squared then is 9. Okay, let's skip down to number 3. The base is 2, so my base is 2. It's saying evaluate that log, which is the log of 16 base 2. 2 to what power gives me 16? Well, that power would be 4. So 2 to the 4th is 16. And then the bottom one's a little trickier because it does have that square root. So really what you would want to do is rewrite that one as 5 raised to the log of 5 to the 1/2 power base 5. So this is saying 5 to the 1 to what 5 to what is going to give me 5 to the 1/2? Well, 5 raised to something has to give me 5 raised to the 1/2, so that has to be 1/2, which is where that 1/2 right there comes from. So 5 to the 1/2, and again, which is 1/2 power is a square root, we write as the square root of 5. I'm hoping what you're seeing here, and this is the shortcut, if the base is 5 and the base of my log is 5, my answer is the argument, and it works every time. The base is 3 up here in number 1. The base here of the log is 3, which I'm raising it to. The answer is the argument, number is 9. And hopefully you'll start to see the pattern over here on 5, 6, 7, and 8. So I've got a log base 5 of 5 to the 3rd. The base and the base are the same. And what this is saying is, if that's the same, what you get out of it is the exponent, which is 3. Because ultimately this says 5 to some power equals 5 to the 3rd. That's got to be 3. This is saying, number 6, 7 raised to some power has to give me 7 squared. Well, what's the power? The power is 2. 2 is the answer. 3 raised to some power has to give me 3 to the 4th. Well, the power is 4. 3 raised to some power must give me 3 to the negative 2. The answer is negative 2. Okay, you can go through the middle steps if you really want to, but ultimately that's what you're looking for. Are the bases the same? If the bases are the same, you're looking for the exponent or the argument, depending on which one it is. So hopefully you guys can see that. So ultimately, the properties here, property number 1, a raised to the log of n base n. So it's a raised to the log base of a. Actually, that's a typo. That n right there should be a. Boy, that's way off. Let me try that again. This should be an a, not an n. So get rid of that. And that should be base a. Here, let's just rewrite it. A log base a of n. That's what that says. And if that's the case, if I have the same base here that I have here, it's going to equal n. So that equals n. So if I have a log base b, same base here, that should also equal n. It'll be the exponent. So log base b raised to the nth power equals n. All right, so hopefully you guys can see that in these next ones. These should be pretty easy now that you kind of have that. Normally I'd like to give you guys a little bit of time to work this out, but since I can't just stand here and record this video and have it just sit here for a couple minutes, I'm just going to walk through it. So this is a log of base 8, where this is the base of the exponent. So log of 8 to the 7th, base 8, is just going to be 7. Again, I really hope you guys are seeing this, because this is actually one of the easier things to do. And the second one down, now the log is in the exponent, but the bases are the same, so it's the base 7, it should just equal 4. Okay, the one on the upper right here, log base 82, the base of the exponent is 82, so the answer is 1/2. And then hopefully you guys can figure this out, because nobody really wants to try and figure out 1,234 raised to the log of 1,000 base 1,234 of 34. It's just 34. All right, so you guys will need to know that one. Again, I don't think that those are too difficult once you understand the pattern that you're looking at. There are some things that we're going to do, that we're going to throw in there, that's going to change some things up a little bit on there, but we'll figure that out as we go. Okay. So, the power property. What this says is and this is where I gave you guys the properties right in the very beginning of class. Remember that logs are exponents, they follow the same properties as exponents. Really, this log right here is an exponent without the part that's being raised to the n. So what it says is I have an exponent raised to another exponent, n. If I raise an exponent to an exponent, if you go back to the first set of notes that I gave you right in the beginning of class, if I raise an exponent to an exponent, I'm really multiplying the exponents together. Well, you can do the same thing here. I can multiply that n times that log. Ultimately, what you want to know is if you have an exponent on your argument right here, you can bring that exponent to the front of the log and multiply it. And that's what you're doing. So I can bring the exponent of the argument a out to the front and multiply it times the log. So, example, log of x cubed base 6. I do have an exponent on my argument. The exponent is 3, which says that I can bring that 3 to the front of my log and multiply it. So I can have that as 3 log of x base 6. And they mean the same thing. Properties of exponents. If you raise an exponent to an exponent, you can multiply the exponents together. So how does that help? What it helps us with is actually solving equations. All right, and there's a couple of different things that we can do here. If we know that the bases are the same, so let me just give you a quick example. Actually, I'm going to move this back up for a second. If I know that I have 3 to the x, and that equals 3 to the 7th power, it should hopefully be very intuitive that x has to be 7. Because the only way that 3 to the x is going to equal 3 to the 7th is if these two exponents are equal to each other. So we can say that because the bases here are identical. So what we're going to do is we're going to try and get the problems that we have down here to be exactly the same base. And we're going to use properties of exponents to do it. This is where you kind of have to be good with your multiplication skills, because you have to recognize 9 as being a power of 3. 9 is the same as 3 squared. So we can rewrite that as 3 squared to the x power, because 3 squared and 9 are the same. You also have to recognize 27 as being a power of 3, because 27 is 3 cubed, and we're going to raise that to the x minus 1. Now the bases are the same. I've got 3 to some power equals 3 to some power. So really what I can do is I can figure out what makes those powers equal to each other. Well, the first thing is I have an exponent raised to an exponent over here on the left, so I'm going to multiply the exponents together. So this is really 3 to the 2x. Same thing on the right one. You got to remember that this x minus 1 right here is like in parentheses. So you got to distribute when you multiply. It's 3 times both of those. So that'll really be 3 to the 3x minus 3 power. Again, bases are the same. If the bases are the same, that means the exponents must be equal to each other. So how do I solve? I'll set the exponents equal to each other. And then I'm going to solve that equation. That'll tell me the value of x that makes this true. So to solve that equation, it looks like I would subtract 3x on both sides, and I would get negative x equals negative 3. But I'm not solving for negative x, I want positive x, so I should divide both sides by a negative 1, and we get that x equals 3. And if you plug that back in, you can actually check this in your calculators. You plug in 3 here and here, you would get 9 to the 3rd power, and you would get 27 to the 3 minus 1 power, which is 27 squared. 9 to the 3rd power and 27 squared are exactly the same thing. And again, go ahead and plug that in and check it out. I think you get 789 or 729, something like that. 729, I think, is it. But you can check it. Okay, same concept over here on the second one on the right. Hopefully this one's a little bit easier because you should know that 16 is a power of 4. So I can make the bases the same real easily. So I'm going to rewrite this 4 to the x plus 4. That's the left side. I didn't do anything to it. And 16 we can rewrite as 4 squared. So now the bases are the same. Both of them are a base of 4. I can set the exponents equal to each other and solve. So x plus 4 must equal 2. Subtracting 4 on both sides gives me that x equals negative 2. And there's the solution, because if you plug negative 2 back into the first one, you would get 4 squared, which of course is 16. Okay, using properties of exponents to get the bases to be the same. Again, you have to be good with some of your multiplication, raising things to powers. You're going to have to be able to figure those things out. And most of this is going to be expected to be done without a calculator on tests. So make sure you're good with this. Option 2. Same idea, but we really need to, because the variable is in the exponent, we're going to have to come up with a different way, because if you look at this, the base here is 2. 25 is not a power of 2. Okay, you can raise 2 to whatever power you can think of off the top of your head, not a whole power of 2, and you're not going to get 25. So I can't rewrite 25 as a power of 2. Well, there's another way to do it. I can change this whole thing into logs. So the idea is, isolate this term first. Isolate the term that has your x in it. Well, there's nothing else there. It's just 2 to the x, so that's isolated, so we're good there. Go through the property that I told you to before. Change it into a log. We went through this the other day. Hopefully you've done your homework and figured some of this stuff out. Remember that a log is an exponent. So the first thing I'm going to write is log of something equals the exponent. Well, the exponent here is x. Now, hopefully you guys remember, what's the base? The base is 2, so that's the base of the log, which only leaves what I'm taking the log of, which is 25. If you're not sure, you can always double check by doing the little circle pattern. 2 to the x equals 25. That matches exactly what we have here, so that would be correct. And lo and behold, we've actually solved for x. X is the log of 25 base 2. Now, what is that as a decimal? I don't know. But it's actually asking us for an exact value. What I have given is an exact value. It really doesn't have a lot of meaning to us because we don't really understand what the actual value is. But that's the concept. So now we have the exact value. X is the log of 25 base 2. That's the answer. At some point in time, we're going to be asked to approximate this as a decimal, which means you'll be able to plug it into a calculator. But for now, that's it. All right, the second one. The second one says e to the negative x minus 4 equals 12. Well, the variable, again, is in the exponent, right here, but it's not isolated yet. It's not all by itself on one side of the equation. So in order to do that, I need to add 4 to both sides. So I'm going to get e to the negative x, adding 4 gives me 16. 16 cannot be put into a nice, common, easy base of e. As a matter of fact, it's one of the harder things to do. Hopefully you remember that e is the base of the natural log. And if you don't, just remember, you're going to have to know that one. E is the base of the natural log. So when I go to write this, I could write log with a base of e, but I'm actually going to write natural log instead, which again is ln, not nl. Again, I don't know why, but that's the way to do it. So I'm going to write natural log of something equals the exponent. Well, the exponent is negative x. Okay, the base is e, not typically written, but for now, go ahead and write it. It's okay. and I am taking the natural log of 16. Again, double check your answer. E to the negative x equals 16. That matches what we have, so we're good there. I'm going to erase that. One more. Two more. There we go. But I haven't actually solved for x. What I have is negative x. So in order to solve for x, once again, I just need to divide both sides by -1. So what I get is that x equals the negative natural log of 16. And notice I don't need to write the base, because the only base of a natural log is e. I'm going to rewrite that a little bit better. There we go. You can write the e as the base. You don't have to. I will typically not do that. Okay, one more of these. 2 to the x minus 4 equals 24. 24, again, is not a power of 2. Yes, you could multiply 2 times 24 and get, 2 times 12 and get 24, but that's not what they're asking. It's 2 times itself. How many times will get you 24? It's not going to work out to be a nice power. So again, the exponent is in the variables in the exponent, So we're going to go ahead and rewrite this as a log. The base is 2, so it has to be a regular log. It's not a natural log. So the base is 2, so it's going to be the log base 2 of something equals my exponent, because logs are exponents. So I've got to take the log of 24. And again, double check it with a little circle pattern to make sure that's right, and it is. I have not fully solved yet for x. In order to solve for x, I would have to add 4 to both sides of the equation. Now, I want to show you guys something on this because it's kind of important. What I'm getting ready to write is incorrect. This is not correct, so don't write this. Hopefully you guys can see what I wrote there was the log of a log base 2 of 24 plus 4. The problem with that is I don't know if I'm taking the log of 24 plus 4 or the log of 28, or if it's the log of 24 and then I'm adding 4 to the end of it. Because of that, we don't write the plus 4 on the right side of the log. We're actually going to write the plus 4 on the left side. So when I add this 4, it's going to go in front of the log. Okay, I know it's kind of a technicality there, but hopefully it makes sense as to why you wouldn't do that, because I don't know if we're really adding the 24 and the 4 as a part of the argument, or whether it's separate when you write it the way I had it the first time. So this is the more correct way to write that answer. And that we've solved for x. Again, don't have any idea what the decimal looks like. It doesn't matter at this point. What if instead we have log equations? Well, the only way to get out of these log equations, well, there's two ways. First of all, this is very similar to the exponential equations. If I have the log, here, let me just kind of write this up here. If I have the log of x, and that equals the log of 10, hopefully you can see, because I've got the log of something equals the log of 10, this x has to be equivalent to 10. So the argument must be equivalent to the other argument. The same idea applies here. I've got the natural log of 2x plus 3 equals the natural log of 5x minus 6. Since I have one natural log equaling another natural log, whatever the arguments are, they must be the same. So I can solve for x by simply setting the argument equal to itself. And then we'll solve for x. So let's see, algebraically, let's subtract 2x on both sides. And then we have to add 6 to both sides. And then we have to divide both sides by 3. So x would be 3. Now, very, very important. When you are taking natural logs in your equations and you get an answer, you must check the answer. Because if you guys remember, the domain of a natural log or a log is x is greater than 0. You do have that on the stuff that we did the other day. So when I plug, that doesn't mean that the value here, that doesn't mean that this has to be greater than 0. What it means is when you plug that back into here, and when you plug that back into there, what you take the natural log or the regular log of has to be bigger than 0. So if I plug 3 in, I'm really going to get, what is that, the natural log, 2 times 3 is 6 plus 3, the natural log of 9. And over here I'm going to get also the natural log of 9, which makes sense. Both of those are positive values, so we're good. 9 is a positive value. All right, same idea on the one on the right. I've got the log of something equals the log of something. Set those two somethings equal to each other and solve for x. 10 minus 6x equals 8x minus 18. Let's add 6x to both sides, and then we'll add 18 to both sides. Oh, this one works out nicely. And then dividing both sides by 14, we get that x is 2. Once again, we have to double check to make sure that this is okay. So I'm going to take 2, and I'm going to plug it back in for x here, and I'm going to plug it all the way back in for x up here. So if I do that, let's see, plugging 2 into the first one, that's already going to be a problem, isn't it? It's going to be log of 10 minus 12, so that's log of negative 2. That doesn't exist. You cannot take the log of a negative number. The domain of a log is x has to be greater than 0. Negative 2 is not greater than 0. What that tells me, even though it looks like I got a solution here, is that there is actually no solution to this problem. Because I cannot take the log of a negative number. Ironically, I think if you plug 2 back into the other one, you would also get the log of negative 2. While those two things actually equal each other, at least it looks like they do, neither one of them exists. So you can't do it. Does not work. No solution. You gotta check your answers when you plug stuff back into logs. When you plug stuff back into exponentials, you don't have to check it because exponentials can be raised to any power. When you plug stuff back into logs, when you solve for logs, you're going to have to check it. All right, almost done. And then you guys will be able to get busy on the homework. All right, when one side has a log but the other side doesn't, that's what we're going to do here. So the idea is you want to isolate the log, meaning get the log all by itself first. The log over here is not isolated. As a matter of fact, it's got a 5 out in front of it. So in order to do that, we're going to have to divide both sides by 5 first. Log of 7x base 2 equals 4, dividing both sides by 5. Now that the log is isolated, this is actually really simple. This is 2 to the 4th equals 7x. Rewrite it as an exponential. The only way you can get that x out of the argument is to rewrite this as an exponential. So it'll be 2 to the 4th equals 7x. Okay, 2 to the 4th we can figure out. I think that's 16. But in order to actually solve for x, you would divide both sides by 7. So we would get that x equals 16 over 7. Now, you do have to plug that back in, 16 over 7. If I multiply 7 times 16 over 7, I'm going to get the log of 16. Either way, it was a log of a positive number, even if you couldn't figure that out that quickly. It's okay. We're good. So that one checks. Okay, same thing with natural logs, the one on the upper right here. That's not isolated yet. I need to isolate it, which means I need to divide both sides by 2 because it's 2 times the natural log. So if I divide both sides by 2, I get the natural log of 7x equals 1/2. The biggest thing is you have to remember, because it's not written, that the base of every natural log is e. So we're going to write it in just so that you can see it, but it's e to the 1/2 equals 7x. So we'll write that. E to the 1/2 equals 7x. If you can remember it, 1/2 power is a square root, so that's the same thing as the square root of e equals 7x. And I still need to solve for x, So I'm going to divide both sides by 7. So what we get is x equals the square root of e divided by 7. Be careful not to put your square root over the whole fraction because the 7 is not under the square root. All right, almost there. Once again, I have a log equation. I need to isolate the log first. And I believe that that's supposed to be the log of negative 2r. That should probably be in parentheses. Base 7. Have to divide both sides by 2. Don't get confused by this. Dividing by 2, I'll actually write it out here. 2's go away. Whoops, missed. 2's go away there. 0 divided by 2 is still 0. So you're going to get the log of negative 2r base 7 equals 0. And you might be thinking, wait a minute, I thought you said a log can't have a negative number in there. If r is positive, if r itself is a negative number, this is going to be okay because then you'll get a positive inside. So we still have to solve for r first. Well, this means 7 to the 0 equals negative 2r. Well, 7 to the 0 equals negative 2r. Remember, anything to the 0 power is 1. So that's 1 equals negative 2r. Dividing by negative 2, you get that r equals negative 1/2. And if I plug negative 1/2 back into here, negative 1/2 times negative 2 gives me a positive. So I'm taking the actual log of a positive number. So we're good. One more. Looks like we have to divide by negative 6 on both sides here. So we're going to get the log of x minus 3 base 3 equals 4. And then it's 3 to the 4th equals x minus 3. 3 to the 4th equals x minus 3. 3 to the 4th is 3 times 3 times 3 times 3, which is 81. And then to solve for x, we're simply going to add 3 to both sides, so we get x equals 84. And if you plug 84 back into that x right there, you would get you're taking the log of 81, which is fine. It's a positive number. All right, so there you guys have it. A little bit less than 40 minutes of lecture notes. So again, I really apologize. I could not be here with you guys today, but I didn't want you to miss out on your lesson. So here it is. If you have any questions, I will do my best to answer them when we come back on Monday. Also, this is going to be up on Google Classroom. So if you need to go back and rewatch it to be able to do your homework, you have that, you'll have that option. So it'll be there for you guys. All right. Have a great weekend. I will see everybody next week.